Okay, so you can see this one. So in the last class, I was discussing about uh, source follower. After followed by the source follower, so we have seen the difference between three different amplifier characteristics and what is input resistance, open circuit voltage gain of the amplifier, as well as voltage gain, as well as the overall voltage gain of the corresponding, and we have tabulated the three different configurations. So common source is and follow, and we have compared them analysis, and we have seen that these are the main important aspect which you need to see when you are going to characterize any amplifier. So in this common source, so you'll be having the output of the gain will be 180-degree out of phase, and the output voltage will be 180-degree out of phase. Because of that, you are going to get a negative sign. So for both common source, you will be having the negative sign over there. Whereas in the source follower, we're going to get the output as well as input, both are same. Hence you can see there is no change in the direction. So output voltage as well as input voltage will be both appearing across the input side, as well as the output side will be nearly equal. Hence you will be getting the voltage gain to be as a 1. So followed by that, we have seen what are the different capacitive effect, so that the MOSFET are going to have. So internal MOSFET capacitance. So whatever we have derived these expressions and all, so for the gain calculation, input resistance, output resistance and all, so we have just considered the MOSFET to be operated with them in the midband frequency range. So in the midband frequency range, I just discussed today. So what do you mean by midband frequency gain and all? So in the midband frequency, where you will be getting the maximum gain. So in that, when you are going to get the maximum gain, so this equation holds good whenever you are going to have them MOSFET to be acting like an amplifier. And when we are going to consider this MOSFET as an amplifier, so we are going to consider the MOSFET is to be operated at the midband frequency gain. So why we are going to get, we'll just tell. Okay, so that is about the amplifier. So when we are going to have when the input signal is of low frequency, or if it is a very high frequency, you can see some of the effects, that is capacitive effects, that is going to be absorbed, because of which the gain will not be a constant parameter. So the gain is going to vary with respect to input frequency. So input frequency of the input signals, or it is going to vary with respect to different frequency bands. So at the lower frequency band, if the frequency of the input signal is low, or if the frequency of the input signal is very high, then also you are going to get the frequency, the gain going to be get deviated. So because of that, we can say that the frequency is dependent upon the gain is dependent upon the frequency, and we have derived this expression when the gain by considering the gain expression independent of frequency. So in the derivation modifier, so when we are going to derive the characteristics of the parameters for common source with source resistance as well as source follower, so we have not considered the frequency effect. So because of that, we are going to get the gain expression as this. So when you're going to get this gain expression, so you're going to get the maximum gain. Okay, so when we are going to have a gain to be at low frequency as well as at a high frequency, you can see there is some of the effects. So in that, we are going to consider the some of the internal MOSFET capacitance, so which will be usually, it will be absent, or it will be in the open circuit forms. Okay, so internal MOSFET capacitance which will be usually inactive in the low frequency operation of the signal. So those low frequency capacitance, those internal MOSFET capacitance will start become conducting when it is going to operate in a lower high frequency. So whenever we're going to discuss about the high frequency model and all, so we're going to consider the capacitance effect. So with the high frequency, these internal MOSFET capacitance will cause the gain to getting roll off. So because of which, you're going to consider what are the different capacitance associated in the MOSFET. So when we are going to discuss, it has been broadly classified into two main types. So one is what? So gate capacitance. So that is because of the structure of the operation itself. So metal oxide semiconductor. So metal as well as semiconductor acting like a parallel plate, and between that you are going to have an insulator as a insulating material as a silicon dioxide. because of which whatever you apply the voltage and all, so you can get the charge getting accumulated, because positive charge apply moderate, so you'll be getting negative charge getting accumulated. If you're applying a negative charge, so you're going to get a positive charge getting accumulated over here. So because of which so the gate itself acting like a parallel plate capacitor. So when you are going to consider the gate in the MOSFET, so you can see the gate and source as well as gate and drain. So these are the two capacitance which you're going to consider in the gate capacitance. So that is the one MOSFET capacitance is because of the gate capacitance effect. Another capacitance effect which you can observe here is so you can see the source as well as the drain region both are made up of a heavily doped N-type material. So in the over the parent P-type substrate, you can see this is a P-type substrate over which you are going to have two heavily doped regions made up of what N plus and N plus. So N plus whenever you know that whenever you're going to have a highly concentration N-type metal and a P-type substrate are there, so here the majority carriers or holes will start moving towards this one, and here the electrons majority carriers will start moving towards here. So because of which you can see some junction to be getting developed between the source as well as the drain region. So because of which reverse bias diode, so it is going to be acting like a reverse bias diode, and because of which you can see N plus P and N plus P, which is going to have a high resistance, and because of which you're going to call the term N plus P and N plus P. So you can say that there is a reverse bias junction diode. So junction has been developed, has been created between these source and drain. So because of which we're going to classify the internal MOSFET capacitance to have one gate capacitive capacitance along with the junction capacitance, and by considering this gate capacitance, we are going to have gate to source as well as gate to drain. So that is going to be operated. How it is going to vary? So with the different regions of operation, that is triode region as well as saturation region. So in the when the MOSFET is operating in cutoff region, so there are three regions of operation of MOSFET, right? So whenever it is operating in a cutoff region, so obviously there will be no charge getting induced because of the voltage. So since it is not able to generate, or it is going to induce a channel between the source and drain, so in the cutoff region, so if it is not having minimum of threshold voltage, then there will be no charge getting induced over here, because of which there will be no capacity effect whenever it is going to operate in cutoff region. So cutoff region only capacity effect will be zero. So CGD or CGS both will be equal to zero. Whereas when you're going to operate the MOSFET in the triode region as well as saturation region, so you can see the operation by pictorial representation of the triode region operation, wherein which you can see the as you increase the gate to source voltage, so that is whenever the gate voltage is very much greater than compared to the drain voltage, so obviously the MOSFET is going to be operated in linear region, and you can see some channels, and there is some charges getting accumulated below the gate because of the application of the positive gate voltage. So this is n channel enhancement. So whenever you apply the positive gate voltage, so all minority carriers will start attracting. So this is going to create a channel that is going to have inverted into n-type channel. P-type substrate has been inverted into n-type channel, so becomes a conducting between the source and drain. So you can see there is a straight line which is going to connect. So only because of the application of the gate voltage, so you can see there is a channel getting established. And if you consider the gate capacitance, you can say CGS and CGT should be equal to half into W into L into, so this is L and this is W, so W into L into 1 by 2 into CGS, so the COX is the limit, this is a capacitance, so into COX, so half of that is given for the CGS effect and half of that it is given for the CGD, so half into W into L into COX, that gives the value for the gate to drain capacitance. So now if you move to the next regions of operation, that is the saturation region of operation. So in that MOSFET, we can say that the gate drain voltage is very much higher when compared to gate to source voltage. So whenever you are going to have a drain voltage very much greater than gate to source voltage, you can see the channel getting pinched off at the drain end. So as you move from the source to drain, you can see there is a tapering of the channel region, and finally you can see some of the channel is not going to be connecting between the source and drain. There is a breakage of this channel, so that is across the drain end. So this indicates what? So that is drain to source voltage is greater than effective gate to source voltage, because of which so the inversion of the layer will not takes place. So because of the heavy drain to source voltage. Because of this heavy drain voltage, so it is not going to create the channel. So before creating the channel, so it is going to be collected across the drain terminal because of high voltage. Hello, Yarar, kindly mute yourself. Okay, so you can see the contribution of CGS and CGD now we can able to see. So in this some of the hello, Amutavalne, kindly mute yourself. Okay, so you can see this is the length of the channel, and this is a length getting pinched off. So part of the channel getting pinched off over here. So if you consider, so you're going to consider this as the length of the channel, means two-third of the capacitance effect is because of the gate to source, because across the source and the, since the source is going to be connected to ground, so it is not going to be affected, and we are not going to apply any, only we are going to apply it will across the source, and we are going to have only gate voltage to be appear. So because of which the inversion takes place across the source, because the source terminal is connected to ground, whereas across the drain end, so even the drain voltage is applying is with the positive, so you can see some of the channel getting pinched off across the drain end, and we can see some of the contribution of CGD is one third of the COX. Okay, so one third of W into L into COX, that gives the value when the device is operating in saturation zone. And we can say some of the source as well as the drain region. So you can see this much of area it has been overlaid by the drain and so you have to add that overlay capacitance effect. So because of which you can see mm, that overlay capacitance effect. So that is also to be included in gate to source as well as gate to drain capacitance effect. So that is going to slightly reduce the value of the capacitance. Okay. So now if we consider what is the next capacitance, that is the junction capacitance. So junction capacitance effect, if you are going to consider, so the junction capacitance is because of the depletion layer that is going to be exhibited between the source as well as drain region with respect to p-type substrate. So you're going to have a two reverse biased PN junction. Okay, two reverse biased PN junction means because formed between each with the source and substrate, and drain with the substrate, drain region as well as source region with the p-type substrate. So it has been given with this formula. So that is whenever the body terminal, if it is left free, so there will be zero body effect will be there. So because of which you can say that the body terminal is if it is not connected, means so it is going to act like a backgate. So because of that, if it is going to act like a backgate, so it is going to vary, or it is going to affect the characteristics of the current. So that is a drain to source current to affect modata. So if it is just slightly positive or positive voltage, means all the, because of that positive voltage, so it is going to attract the charges, that is negative charges towards the body substrate. So because of which you need to apply more and more gate voltage. So across the gate terminal, more and more gate voltage you have to apply in order to establish the channel. So because of this back gate, if it is not because of this body terminal, if it is not connected to source, then obviously it is going to increase the threshold voltage. So this increases the threshold voltage in the sense it is going to affect the we need to apply more gate voltage to induce the current. So current form of so more voltage apply ಮಾಡಬೇಕು. So in that case, what is the thing? So current is going to reduce. So current is going to reduce if it is the body terminal is not connected to the source. So that is the we are going to find out what is the capacitance associated with that. So that is given as a CSB. So CSB as well as CDB are nothing but both junction capacitance existing between source and body and drain and body. So source and body CSB is being given. So CSP 0. So whenever the it is a zero effect, so that is whatever the capacitance effect is there. So that is given as the CSP 0. So that is the junction capacitance whenever the body is connected to source, or if it is connected to ground. So that is the value of CSB at zero body bias. So zero body bias andre, so zero andre we are not applying anything. That means the source substrate is connected to the source terminal. So when the substrate is connected to the source terminal, whatever the capacitance which you are going to have, that is denoted as what? CSB 0. So same way divide by, so 1 plus VSP divided by V naught. So VSP is nothing but the magnitude of the reverse bias voltage. So magnitude of the reverse bias voltage whenever it is not connected. So some substrate voltage will be there. So that substrate voltage is nothing but a reverse bias voltage. So that is going to increase the value of the capacitance. So VSB divided by V naught. So V naught is nothing but a junction built-in potential. So that is between the N plus and P substrate. So whatever the junction it has been created, that junction potential it will be usually 0.6 to 0.8 ಅಂತ ಹೇಳ್ತಾರೆ. So it is going to be having. So square root of 1 plus VSB. So this gives the value of the capacitance between the source and the substrate with capacitance. And the same way you can also calculate instead of source and body, we can have drain and body, and drain and body at the zero bias voltage. So you are going to calculate the value of the capacitance. So this is about the um, junction capacitance. So junction capacitance are two types of CSB as well as the CDB, as well as gate oxide capacitance are two types. So one is CGS and another one is CGD. So totally four capacitance are there. So because of that capacitance effect, so you are going to see some variations, or it is going to have some variation, and the device is operating at high frequency. So we are going to see this is the different major capacitors. And now if we consider the high frequency circuit model, so high frequency circuit model again, so whatever we have discussed right now, the four capacitance effect, so these capacitance will affect the gain characteristics. As I told, so high frequency ಮತ್ತು low frequency ಅಲ್ಲಿ the gain is going to getting roll off because of this internal MOSFET capacitance. So that is because of at high frequency. Whenever we are going to have high frequency, so we need to develop some model. So because of that we are going to see the performance of the MOSFET. So in high frequency, because of high frequency, or how the characteristics, or how the amplifier output voltage, input current, output current, and all it is going to vary. We need to find out. So because of that, we are going to develop another model, which is nothing but a high frequency MOSFET model. So high frequency antidange, you should remember that. So internal MOSFET capacitance, which we have discussed, so it is going to, we need to consider their effect, because these capacitance will be usually absent, or it will be usually not physically present, and it will be acting like a short circuit during the low frequency range of operation. Andre, when the MOSFET is operating, when the MOSFET is used as an amplifier, and if it is using as an amplifier, and if it is operating in low frequency band or mid band frequency band only, so usually these MOSFET capacitance, that is MOSFET capacitance CGS, CGD, CDB, CSB, all these four capacitance will be usually absent, or it will be short circuit ಆಗಿರುತ್ತೆ. So these capacitance, internal MOSFET capacitance, will not have any impact on the output characteristics, or the characteristics of the MOSFET. So characteristics of the MOSFET andre current melagli, voltage, threshold voltage melagli, so it is not having any it is not going to impact the current or voltage characteristics. So because of that, so the gain was very maximum. But when you make the MOSFET to operate at a higher frequency range of operation, so these MOSFET capacitance will which were usually infinite, that means infinite andre, so it will be acting like a short circuit, so it will become conducting. So whenever it becomes conducting, so it is going to reduce the capacitance effect. So the capacitive value is going to reach from infinity to smaller value. So because of that, so these capacitance will reduce the gain, or it is going to reduce the output voltage, or it is going to reduce the output current. So because of which the gain will get fall across the higher frequency. So that is what we are going to discuss, and we are going to develop a model from small signal model to high frequency model. So high frequency model only, so the amplifier will depend upon the higher frequency. So when we are going to develop a model for high frequency model, so you are going to consider all the capacitance, internal MOSFET capacitance. So internal MOSFET capacitance means, so these four capacitance we need to include when you are going to develop a high frequency equivalent circuit. So the figure 10.12 shows the small signal model of the MOSFET, including four capacitance we can see. So that is nothing but the high frequency model. So this model is used to predict the high frequency response of MOSFET amplifier, and also it is very difficult to analysis for the manually, but we can see. Okay, so this is the high frequency equivalent circuit. Okay, so in this what and all capacitance we are going to include, one is CGS is there, another one is CGD is there. So you can see what and all extra thing. So four capacitance has been included. One is gate capacitance like CGS and CGD. Another is nothing but junction capacitance like CDB as well as CSB. Okay, so these two are the junction capacitance and these two are gate capacitance. So the now the whatever the small signal equivalent circuit was there, so you are having what these are all. If you neglect this CGS, CGD, CSB, CDB, and you can see only the gate to this is a control current source. It was there in the small signal model, right? So small signal model, and between gate to since it is absent, so it will be acting like an open circuit, so it is not getting but gate to source voltage, and for that corresponding current will be flowing, that is GM into VGS, and finite amount of resistance R naught will be there. So because of which you can see this is the small signal equivalent circuit model. So now high frequency equivalent circuit model again, what and all things you are going to have. So you need to have four terminals. So one is gate terminal, another one is the drain terminal. Okay, so here it will be source terminal, and another terminal which will be called as what, body terminal. Okay, so four terminals now we need to include. Because of these two junction capacitance, we are going to have another terminal which is nothing but the body terminal, or it is also called as a substrate terminal. Okay, so normal again ಇರ್ತಿತ್ತು ಗೇಟು ಡ್ರೈನು ಮತ್ತೆ ಸೋರ್ಸ್ ಇರ್ತಿತ್ತು ಸ್ಮಾಲ್ ಸಿಗ್ನಲ್ equivalent circuit ಅಲ್ಲಿ. So now we are going to have high frequency equivalent circuit model. So in this high frequency equivalent circuit model, you are going to have four capacitance. So two gate capacitance and two depletion junction capacitance. So it is nothing but a drain to body as terminal as well as a source to body terminal. So body terminal ಒಂದು extra terminal add ಆಗಿದೆ. So now if we see, so here it is extra thing is normal is GM into VGS, that is what, so control current source. So control current source, so there is a voltage control current source. So this is a voltage control current source in which the current is flowing from drain to source. So for a given supply voltage of VGS, so that is GM into VGS. So this is a control current. So we can see another current source denoted as this. So you have to remember, so this is not GM into VGS, it is GMB into VBS. So it is called as GM means what, transconductance. So this is body transconductance. So this is transconductance, normal transconductance. So it is body transconductance. So B corresponds to body. So body transconductance we have to remember. So this is the body transconductance for the given voltage across body to source. So between the body and source, whatever the voltage body and source terminal is there. So because of the body terminal, if it is not connected to source terminal, then this will be acting like a back gate anta ಹೇಳಿದ್ರೆ. So back gate anta ಹೇಳಿದ್ರೆ, so front gate ಅಂದ್ರೆ ಏನು, it is going to have what, gate to source, that is front gate to source voltage ಏನಿರುತ್ತೆ. So because of which it is going to control the output current GM, which is nothing but GM into VGS. Now back gate ಅಂದ್ರೆ ಇನ್ನೊಂದು body terminal, it is also going to act like a gate. So this body terminal also, it is going to control the current. So it is going to reduce or increase the current. So because of which you can see there is a controlled voltage control current source, which is nothing but a body transconductance denoted and to multiply with the body source to voltage. So body source to voltage, so VBS is going to have. So VBS, you can see this is VBS and this is VGS, and you can see this is a negative voltage. If it is there, then obviously it is going to reduce or increase the value. So because depending upon the voltage across the body terminal, so this body source voltage, it is going to control the output current. So that is denoted as GMB into VBS. So GMB is what, so GMB is body transconductance. GM means normal transconductance. So GMB means body transconductance, and VBS is nothing but a substrate to body. So sorry, body to source voltage, which is going to control the current. Hence GMB into VBS we are going to have. Is it clear? And left out with what? So finite amount of resistance or not, and CDB, CSB. This is the two junction capacitors we are going to have. So this is the high frequency equivalent circuit to include these four capacitance affected, and the four terminals we have to write for this high frequency. Now whenever you're going to discuss, so normally, so MOSFET or amplifier, when you're going to have, so body terminal will be usually connected to the source. So when we are discussing the common source or common drain or any type of amplifier configuration, common source, common gate or common drain or any type of amplifier configuration ಮಾಡಿದಾಗ, So we have considered that the body terminal will be usually connecting to the source terminal, so that in order to reduce the effect of body on the device characteristics, so body terminal will be usually connected, will be usually shorted to source terminal, so that it is going to avoid the non-linear ID characteristics. So IV ಮತ್ತು current ಮತ್ತು voltage characteristics ಇದೆ, so it is going to affect. So because of which the body terminal will be body effect and we will be calling it as a body effect. So that body effect is going to affect the characteristics of the MOSFET. So because of which we are going to short the substrate terminal or the body terminal to the source terminal. So that it will be always usually connected to the most negative power supply in the case of N channel enhancement, whereas in the case of P channel enhancement MOSFET ಅಲ್ಲಿ ಏನ್ ಮಾಡ್ತೀವಿ, so it will be usually connecting to the most positive power supply, that is the VDD. So in the case of N channel, it will be connecting to the VSS. So when we do that, so you are going to avoid these two, this substrate and body terminal, and this substrate and the body voltage you are going to remove. So since the body terminal will be usually connected to the source, so these effects will not be there. So because of which source to body voltage drop will not be there, and there is a CSB effect will also be getting reduced. And then so since the source and the body will be shorted, so you can expect the drain and body potential to be exited, and these two capacitance will be usually, it will be there. Okay, CGS as well as CGD. So one important thing you should remember is, so since there was no feedback in the previous small signal equivalent circuit model, right? So previous small signal equivalent circuit model only, so we were having what? So VGS, between VGS we will be having open circuit, and output will be having what? So GM into VGS irtittu, and output only resistance, finite amount of resistance will be was there, but there was no connection between the output to input. So drain ಮತ್ತೆ gate ಮಧ್ಯದಲ್ಲಿ, so we were not having any feedback path. But now with the internal MOSFET capacitance effect, you can see this CGD, that is the gate to drain capacitance, which is going to connect a path between the gate terminal and drain terminal. So whenever you're going to have any feedback path from the output to input, obviously, so here in this case it is obviously it is going to have what? The gain will able to control. So the gain will be able to control. So in this case it is what? Drain ಮತ್ತೆ gate ಮಧ್ಯದಲ್ಲಿ, if you are going to establish any capacitance, so in the drain to gate feedback mechanism ಅನ್ನು ನೋಡಿದ್ವಿ. So drain to gate ಮಧ್ಯದಲ್ಲಿ ಒಂದು resistor which we connect, then that mechanism is going to have what? Negative feedback. The same way here also, ಮತ್ತೆ drain ಮತ್ತೆ gate ಮಧ್ಯದಲ್ಲಿ you are going to have one capacitance between the drain and gate terminal. So when you are going to have any feedback path from drain and gate, so it is nothing but a negative feedback. So negative feedback ಆಯಿತು ಅಂದರೆ, so the gain in the mid-band frequency ಅಲ್ಲಿ ಜಾಸ್ತಿ ಇರುತ್ತೆ. So when you employ a negative feedback, so we have seen common source with source resistance ಅನ್ನು ನೋಡಿದ್ವಿ. So source resistance was acting like a negative feedback resistor action. So because of which the gain was reducing by a factor of 1 plus GM into RS ಅಂತ ಹೇಳ್ತಾ ಇದ್ವಿ. So here also, if you are having any feedback that is going to have a negative feedback, so obviously the gain is going to reduce in the higher frequency because of this MOSFET capacitance. Okay, so because of this MOSFET capacitance CGD, which is going to connect between the drain and gate, so because of this acting like a negative feedback path, and it is going to control the gain. So controlling the gain means it is going to, we're going to have a reduction in the gain. So reduction in the gain because of this feedback action of this CGD. So you are going to have a reduction of gain. So reduction of gain takes place at high frequency because of internal MOSFET capacitance. And now the modification in this also is there, which is going to have, this is the final equivalent circuit of the high frequency. In this value of the drain to body terminal, it is also not going to affect too much at a high frequency. So because of which you are going to remove this also, and you are going to have only gate to source as well as gate to drain capacitance, and on control current source, and one finite amount of resistance you are going to have in the next figure. So in the figure C, you can see the equivalent circuit model of B with the CDB neglected for simplifying the analysis ಅಂತ ಹೇಳಿದ್ದಾರೆ. And simplifying the analysis in the sense this is not going to affect too much for the device characteristics, so it is going to be removed, and we are going to simplify the analysis of this so that we are going to have what? So we are going to have this model. So that is the high frequency equivalent circuit model of the MOSFET. So gate to source, one gate junction gate so this is the gate capacitance CJs and CGD is there, and together with this. Suppose if you neglect, if you remove this these two capacitance, what is going to have? So you're going to have, if the CGD, if you are going to remove, means it has become open circuit, right? So that means you're not going to have any connection between gate and drain. So this path if you remove, as well as this gate to source capacitance if you remove, so the final circuit will be resembling what? So the final circuit will be resembling like a small signal equivalent circuit. So you will be having gate and source will be, it will be there. So this will be, if you remove this, it is going to be CJs will not be there, as well as CGD if it is not there. So finally you will be having the gate terminal, source terminal, between that you will be having gate to source voltage, and from the drain and source you're going to have a current control current source GM into VGS, and finally the output resistance is going to have finite amount of resistance, that is a R0. So this is nothing but a resembling of a small signal equivalent circuit. So if you provided that these two capacitance should be removed, if you are going to add these two capacitance, then obviously the circuit equivalent circuit model will be resembling to that of high frequency equivalent circuit model, because the internal MOSFET capacitance have been considered. So now the modification in the small signal is what? So that is a T equivalent circuit model. So the simplified high frequency equivalent circuit simplified model T model allenitho. So these two things were not there, right? CGD ಮತ್ತೆ CGS was not there. So you can see one node was there here, and here one control current source GM into VGS was there, one resistance equivalent to 1 over GM was there. So and a finite amount of resistance or not to connect between drain and source was there. So this is T equivalent circuit model. So small signal equivalent circuit in the T equivalent circuit model. So we have developed, and now for a high frequency equivalent circuit again, so you're going to add these two capacitors CGD as well as CJS. So this is the simplified high frequency T equivalent model. So as we have seen for the common source with source resistance as well as a source follower, so we have considered the T equivalent circuit model. So for analysis purpose, we have changed it so that you can see this is a high frequency T equivalent circuit model. So this is what the development of a high frequency equivalent circuit model. So this high frequency equivalent circuit model is going to be asked for 6 to 8 marks in the final exam. Okay, this is very important. So small signal equivalent circuit model ಬರೆಯಕ್ಕೆ ಬಂತು ಅಂದ್ರೆ, so the same thing you're going to add two capacitance over here, so that becomes the high frequency equivalent circuit model. So development of this to have gate capacitive, ಯಾವ gate capacitance ಇದೆ, so what is junction capacitance, so that you should know, and followed by that you have to do this one. Okay, so this is about the high frequency equivalent circuit model. So we conclude by presenting on this table. So what is the high frequency model, MOSFET high frequency model andre ಏನು? So we have tabulated in this one. So this is general with the four terminals: gate, source, drain, body, terminal. So all the capacitance, four capacitance has been incorporated, along with that voltage across this body and source, and current source drawing the amount of current GMB into VBS has been written over here. And for this high frequency equivalent models can be simplified by removing the body terminal to nullify the effect. So body terminal will be connected to source terminal madavaka. So source to body capacitance you are going to remove. Along with that, in order to simplify that, CDB is also going to be removed, and CDB remove after that. So you will be referred with only two capacitance, CJS as well as CGD, and correspondingly we are going to have one control current source GM into VGS, and since the body terminal is not there, so body trans conductance as well as VBS will be absent, and because of which another current which is equivalent to GMB times of VBS is going to be removed, and only the finite amount of resistance or not will be connecting between the drain and the source terminal, and you're going to have the simplified high frequency equivalent model. Along with that simplified T equivalent circuit model also we have seen. So we can see some of the equations which are going to be useful when you are going to solve the numerically. So this is a transconductance. So transconductance will be given with the different three different alternatives we have also seen. So what are the three different expression for the transconductance? We can see mu n C equals W by L, VGS minus VT, or VOV you are going to have. So in place of VOV you are going to have this expression, so that you are going to have this 2 mu n C equals W by L into ID, which will be equal to 2 AD by VOV. So this is a transconductance expression. and how the body transconductance as well as the normal transconductance is going to be related. So Gm will be equal to chi times of Gm. So chi can be ranged between the 0.1 to 0.3, 0.1 to 0.2. So you're going to have a body transconductance as well as the transconductance is going to have a relation. And this is a finite amount of resistance which you're going to calculate. R naught is given by early voltage Vi divided by Ed, and Cjs is to have overlay capacitance effect also. So this is like at two-third when you are going to have. So when the device is operating in saturation, so what is the gate capacitance, gate to source? Two-third of W into L into COX plus W into LOV into COX. It is going to have a capacitance effect. So the CGD is equal to what? So one-third of this one. So one-third as well as this one. So W into LOV into COX. So W into LOV into COX. That is the capacitance effect that you are going to have for only CGD and is when the device is operating in saturation region. And we can say CSP as well as CVDB is given with this equation, and correspondingly a high frequency equivalent circuit, that is a transition frequency. We can see this is the transition frequency which we are going to discuss in the next class. Okay, this is about the high frequency equivalent circuit model. So depending upon that, so I have just solved one numerical with respect to different capacitance. So take down the problem. So from an N-channel MOSFET. So for an N-channel MOSFET with oxide thickness TOX is equal to 10 nanometer, length is equal to 1 micrometer. So W is equal to 10 micrometer. So overlay length is equal to 0.05 micrometer. CDB is equal to CSB is equal to 10 femtofarad. So V naught, that is the reverse bias voltage V naught, junction voltage of V naught is given as 0.6 volt. VSB is equal to 1 volt. So VSB means what? Substrate to bias voltage, which will be equal to 1 volt. VDB is equal to 2 volt. So these are the different values for a given MOSFET has been given. So he has asked you to calculate the following capacitance when the device is operating in saturation. Saturation region ಇದ್ದಾಗ ಎಷ್ಟು gate capacitance CSB is going to have. So we need to find out the capacitance. So calculate the following capacitance. So COX. So for all the things we should know what is the COX. Oxide gate capacitance. COX, how we are going to find? Epsilon naught into epsilon r divided by TOX. Epsilon OX will be equal to what? Epsilon r into epsilon naught divided by thickness of the oxide. So for silicon dioxide, 3.9 is the relative permittivity. So multiply with absolute permittivity divided by so oxide thickness. So that gives the value of the gate oxide capacitance. So if you substitute, you will be getting this value as the oxide gate capacitance. Okay, so 3.45 femtofarad. Okay, so once you know this oxide gate capacitance, so we need to find out what is that. So overlay capacitance, overlay capacitance COV will be equal to what? So LOV into W into COX. So W into LOV into COX. COX already considered way. So LOV over length of this has been given, width also is given. So width is what? 10 micrometer. So length is LOV is nothing but 0.05 micrometer. Multiply with the oxide gate capacitance 3.45 femtofarad. 3.45 is nothing but COX. 10 micrometer is nothing but width. Length is the length of the length, so 0.05. So you will be getting 1.72 femtofarad. And CGS. So when the device is operating in saturation, you have to recall that figure. So two-third of W into L into COX. So two-third of W is 10 micro. So length is nothing but 1 micro. COX is 3.45. So you will be getting with 23 femtofarad. Okay, so this is the value of the gate capacitance. So when you see the what is the value of CGD? So CGD just now we have discussed, right? CGD is equal to what? So CGD is equal to, so when we are discussing the in the overall tabular column, CGD when it is operating in saturation, so you can see W into LOV into COX. So that will be remain same as that what? So W into LOV into COV. So W into LOV into COX, that is 1.72 femtofarad only you will be getting as a CGD. So CSB is equal to what? CSB divided by square root of CSB naught divided by 1 plus VSB divided by V naught. So CSB naught he has given was what? So CSB is equal to CDB is equal to 10 femtofarad divided by offset. So this is a depletion reverse bias voltage zero point 0.6 volts ಇದೆ. So VSB is equal to 1 volt on that. So 10 femtofarad. So he has given this CSB naught. So VSB is equal to 1 volt divided by zero point 0.6 plus 1. So if you substitute the value, so you will be getting 6.1 femtofarad. So same way CDB is equal to what? CDB naught. So CDB naught is remains same as 10 femtofarad. Square root of 1 plus VSB is equal to 2 volts divided by zero point 0.6 you will be getting. So 1 plus 2 divided by zero point 0.6, that will be equal to 4.8 femtofarad per farad capacitance. So these are the ways in which you are going to find out the value. So equations ಗೊತ್ತಿದ್ರೆ ಸಾಕು. So you need to know what is this value, and if you know the value of this capacitance, so easily you can score 4 to 5 marks. Okay. So this simple problem is so simple numerical they will ask for 4 marks. So to find out all the capacitance. So easy to score. Okay, if you know that concept, so if you know that value of this capacitance expressions means easily you can be able to solve that numerical. Is it clear? So with this I'll just conclude today's session. So since I need to start another topic, so it is going to take too much time. So tomorrow in tomorrow class I will just start up with high frequency response of the common source amplifier. Okay, it will take too much of time, so I'll just conclude today's session over here. Okay, 5 minutes early I'm leaving, but I'll just conclude. Any doubt you're having? If you're having any doubt, you can ask. Hello, students. If you're having any doubt, you can ask.
No doubt, sir.
Question paper, model question paper ನೋಡಿದ್ರಾ? So have you seen the model question paper? If you have not seen, I will just I
Yes,
can
sir, we have seen, sir, you have sent in the group.
mm, whether it is required to discuss now. Time if it is there, so I can discuss question paper.
Sir, IAಗೆ portions ಎಲ್ಲಿ ತನಕ?
Up to tomorrow ಅಥವಾ ಡೇ ಆಫ್ಟರ್ ಟುಮಾರೋ ಕ್ಲಾಸ್ ಮಾಡೋ ತನಕ ಇದೆ. ಸೊ 24th ಅಲ್ಲಿವರೆದು 2 ಮಾಡೆಲ್ಸ್ ಕಂಪ್ಲೀಟ್ ಮಾಡ್ಬೋದು. ಸೊ 2 ಮಾಡೆಲ್ಸ್ ಮಾಡ್ಬೋದು ಅಥವಾ ಲಾಸ್ಟ್ ಒಂದು ಟಾಪಿಕ್ ಬಿಡ್ಬೋದು. ಆಸಿಲೇಟರ್ಸ್ ಒಂದು ಆಗಲ್ಲ ಅನ್ಸುತ್ತೆ. ಸೊ ಅಪ್ ಟು ಹೈ ಫ್ರೀಕ್ವೆನ್ಸಿ ಅದೆಲ್ಲ ಲೋ ಫ್ರೀಕ್ವೆನ್ಸಿ ತನಕ ಮಾಡೇ ಮಾಡ್ತೀನಿ. ಐ ವಿಲ್ ಜಸ್ಟ್ ಫಿನಿಶ್ ಇಟ್ ಆಫ್. ದಿಸ್ ವೀಕ್ ಫುಲ್ ಕಂಪ್ಲೀಟ್ ಏನು ಮಾಡ್ತೀನಿ ಅಲ್ಲಿ ತನಕ ಇರುತ್ತೆ. ಓಕೆನಾ? ಹಲೋ, ವಾಯ್ಸ್ ಬ್ರೇಕ್ ಆಗ್ತಿದೆ. ಹಲೋ, ನಿನ್ನ ವಾಯ್ಸ್ ಬ್ರೇಕ್ ಆಗ್ತಿದೆ.
ಸರ್ ನಾನು ಕೇಳಿದ್ದು ಮತ್ತೆ 2 ಮಾಡ್ಯೂಲ್ಸಾ ಫಸ್ಟ್ ಐಎಗೆ?
ಮೋಸ್ಟ್ಲಿ 2 ಮಾಡೆಲ್ಸ್. 2 ಮಾಡೆಲ್ಸ್ ಇರುತ್ತೆ. ಓಕೆನಾ? ಆಲ್ಮೋಸ್ಟ್ 2 ಮಾಡೆಲ್ಸ್ 1.5 1.758 1.8 ಅಷ್ಟಂತ ಸಿಲೆಬಸ್ ಕವರ್ ಆಗಿರುತ್ತೆ ಈ ವಾರದೊಳಗಡೆ. ಸೊ ದಟ್ ಮಚ್ ಓನ್ಲಿ ಟಿಲ್ ದಟ್ ಇಟ್ ವಿಲ್ ಬಿ ದೇರ್. ಓಕೆ, ಎನಿ ಡೌಟ್ಸ್ ರಿಗಾರ್ಡಿಂಗ್ ಟುಮಾರೋ ಟುಡೇಸ್ ಕ್ಲಾಸ್?
ಸರ್